Okay, let's go ahead and go through Lab 5 again. For most of y'all, this will probably be the hardest lab.
Okay.
Just FYI. Well, it's better it's now than later at the end of the semester.
Yeah, we have time to bring our grade back up after.
True. Well, maybe.
Have a month to do it.
Maybe. Okay. What's going on here? Well, now that we have all created, well, I need to update this. Now that we've created all of our components, we need to actually paste them together and run executables. So let me take a step back. We created all our components for our processor. Y'all presented them on Monday. I have created my own versions that are going to work nicely together. And I'm going to provide those to you. I've already provided those to you in the Lab 5 directory. We have talked about assembly and how you take a binary and you produce an assembler. I have given you or written an assembler for you because to make this simple, because a full-fledged assembler is going to be really complicated to try and load. But this one is just a simple assembler to load it in your binary. Your job is to take all these components, put them together, and make an actual single cycle MIPS 32-bit processor for only a couple of instructions. And by a couple, I mean the basic 8 that we've talked about so far. And I've given you an assembler so that you can test your processor out. Now, some of this probably sounds difficult, but it's kind of funny where if there's only about 20 lines you need to do, and then you're done. The problem, what makes this project hard is not the coding part, but sitting down and figuring out what's going on. This is a pure big architecture problem. The problem is the architecture of the system. How do you set up the entire system? It's not can you code it, it's can you think about the whole big picture about how everything is plugging together, how everything works together, and then somehow build it together. That's the point of this project. All right, I give you some instructions. Let me jump over and show you what's going on. So if you look inside of Lab 5, it looks something like this, except for you don't have the old directory because that has all my old solutions to this project. But notice we have multiple .v files. These are your different components. They should look familiar. Adders.v, ALU. We've got a decoder, data memory, instruction memory. The MIPS 32 single cycle test bench, that's to test your MIPS 32 processor. And then the MIPS 32 single cycle, that is your MIPS 32-bit processor. And then you have signExtend.v and regfile.v in your ROM. Those are other components. Now, the two files you will probably have to edit, or actually the only two files you need to edit to get 100 on this lab are your single cycle.v and your testbench.v. And, okay? So, let me go look at the test bench real quick for you. This is the test bench to actually set up your processor. So this is a good part to start because it's a very high level of what's happening. Notice inside of this test bench, we're going to test our processor. We have 3 components. We have a clock, flip, that goes back and forth, tick tock, tick tock. We have a reset line to tell your components to reset, reinitialize to 0. And then we instantiate the processor. Notice the processor just takes the clock and the reset line. That's it. Inside the processor, it's going to manually load your program from memory, so we'll get to that momentarily. One of the 2 lines I suspect you'll edit in this file is one is the find out the clock delay. Right now I have it set to 1 tick. Now you're going to need way more than that, but I'm going to let you try and figure out what that is. Okay. Now do we have? Oh, it's not up there. Oh well. That's okay. Notice the clock is simply toggling between 0, 1, 0, 1, 0, 1, back and forth.
What does it mean by equals not clock? Oh, is that what you just said?
Yeah. Right, if it's 0, then it becomes 1. If it's 1, it becomes 0. That's it. All right, how do I do this? Well, test.vcd set up your GTK wave so you can actually inspect this visually. You will probably be looking at this a lot. Dump everything from the CPU up here. That way you get a handle to every single component that you would possibly ever want. Hold the reset high, initialize the clock to 0, and we're going to hold reset for 10 ticks. That should be enough to reset everything in all your components. So I don't suspect you'll be need to change that. Then we're going to release the reset line and then display we're going to begin simulation. Alright, right now after 100 ticks I call finish. This is just so it actually ends when you're first testing it. But once you're able to load in the halt instruction and execute the halt instruction, you're going to want to take this pound finish, this whole line away. Okay?
Yeah.
Because you'll already be halting somewhere else. So the two places I suspect that you will be changing your code in this file are how long is the clock tick and removing this pound 100 finish. Alright, here's a trick question. How pound 1 on the clock, how many ticks is the clock right now? With this line of code? 2.
2.
Because it has to go up and back down. So it's actually 2. So it's double whatever you write there. Right now it's not written on top, but I have it set to every tick is a nanosecond. So if that means if a clock cycle takes 2 ticks, it's a 500 megahertz clock right now that you are simulating. Obviously, you're going to increase this number, and therefore your clock rate is going to go down. That's fine. Part of this is to show why single cycle is very slow. Hopefully you will discover that out as you're putting this together. Okay, so that's the MIPS 32 test bench. That's the test bench, thank you. Okay, here we go. Now, this is the actual single cycle processor. You're going to see in a lot of your files this time scale up top. Let me explain to you what this means. This is how to tell Verilog what your timing is. AKA those delays you put in there, it's going to signal how much it is. So for the first number is how much that delay actually is. So that 1 ns means that it's 1 nanosecond for every 1 value you put in there. Now, Verilog does allow you to use portions of a full clock tick. So you could do 1.1 or 1.02. But Verilog needs to know to what resolution you want to do that, and that's what the picosecond is. It means every tick is 1 nanosecond. The resolution of your simulation is a picosecond. So in that way, for us, this doesn't matter because we're using whole clock ticks for everything. But just so you know what that second number means, if it's 1 nanosecond over 1 picosecond, you can do 1, you can do 1.1, 1.01, 1.001, because that would be 1 picosecond right there. But if you did 1.0001, that would just convert straight to 1, because anything after that 0 it's going to ignore because that's what your resolution is that you set. Does not matter for this project, but that's what it means because it's written up there.
So when you say we could use those, we could use the top 4 things as like a delay?
Yeah.
Okay. So we could put pound, okay, gotcha.
You got it. Yeah.
Does that change anything that much?
It can,
Okay.
because that's going to show you when things actually move around. Because, yeah, I mean, if it took, instead of 1.0, it took 0.95, that's a significant increase in speed.
But for us, don't listen.
But for us, well, no, it's not don't listen. It doesn't matter for this simulation because we're using whole clock ticks.
Don't touch.
So don't touch that. Leave that alone.
Or sadness will
If you need to put that somewhere, make sure it looks exactly like that on top of your file. All right, module clock, or module, sorry, MIPS 32. It has a clock and a reset line. I have written a bunch of default registers and wires. All right, let me step back and make sure it's very clear what it is I'm asking you to do for this project. Let's see, it does not exist. Oh, that's kind of weird.
That's the worst.
Here. This is what I'm asking you to implement. Alright? You can try and look at the book. The book may help you, but this is what's correct. Alright?
Are we talking about the optional book? Where it does-
No, the architecture book. No, the optional book we're done with.
Okay, it does have that pipeline
In the-
in the C section of the book. C appendix.
Are you talking about the organization? Computer organization and design?
The big thick one?
Yeah, no, that's the required book. There's a required and an optional book. This is in the required book. Patterson and Hennessy?
No, this is in the other book too.
Oh, it is in the other one?
In
Oh, I have not seen it in that one.
The C appendix.
Okay, well, that may help you,
It's-
but this is what's correct.
Okay.
Okay. This is what we're looking for because I had to change a couple things up in order to make it work inside of Verilog correctly. Okay?
Yeah, I'm gonna have to print that thing out, laminate it, and use a wax pencil.
Yeah, you'll probably be staring at this a lot.
Okay.
All right?
So print it out.
Sure, print it out, stare at it, laminate it, put it up on the ceiling while you're taking a
I was just
shower.
thinking, if I print it out, laminate
Yes,
it, and have a
it's
wax
put in your
pencil, I
shower
can walk
somewhere.
myself through.
Because notice there's all your muxes, you got an adder, your ALU, you got a decoder, control ROM, you have memory, register file, more muxes, instruction, PC, adder plus what, right? It's all, I've given you all these components. Your job is to piece them together.
Right, so we don't need just one mux, we need 1, 2, 3, 4 muxes.
You got it. And now you also got to pick which mux you need to be using at each point.
Oh, yeah.
So we need to implement everything there.
Right, so, just to be clear,
So
back in here,
everything should have.
you have, I've given you all those components. I've set up, notice I have a register for PC and for 1. Hey look, there's PC, there's 1.
Yay.
Alright, I gave you that. I have given you suggested wires. You can use these, you can delete them and use your own. Whatever you want, I've left these in here just to help you out. If these are too confusing, ignore them. But if they help you out, great.
My question is, are those just a few of the wires? They're not all the wires?
I'm not going to guarantee that these are all the wires,
Right.
but these definitely is at least a majority of them. This is the data flow model where we just have next PC is PC plus 1. We're not using an adder there, so I've actually done this part for you with data flow. Actually, I've done PC plus 1, and then it goes right back into PC, so I haven't put in the mux for you yet.
So you just got to put it in the mux.
You gotta put in the mux. But you gotta figure out why we have a mux there, when you hook up the mux, etc., etc. Here's where the majority of your coding will be. What's that?
I guess the PC.
What's that?
Where does it start? There's no like. I guess PC is the start of it.
So yeah, that's why this is an architecture problem. Remember, all this is happening in parallel.
Yeah.
We're gonna die.
This is this is a completely different type of problem than what you're used to. Well, not
So
completely.
actually, would the 1 be the start point?
There is no start point.
Oh, because we're in a cycle.
There is no start
We're in a
point.
cycle, don't
Do we all need to like stand up and repeat after me? There is no start point.
Everything has an input.
Yeah, everything has an input. Yeah, it's one giant circle, guys. There's no. I mean, you can think of it. Obviously, it's flowing from left to right, so you can think of it as you get an instruction, you do what you want with it. Hopefully, you go to the register file. You might be manipulating a couple things. It comes back, and then you need to read the next instruction at some point. How do you determine when you're done with one instruction and you begin the next one? What do you use?
Your brain.
What does the processor use to? What do you use to tell the processor you're done with this instruction? Go to the next.
PC.
Not the PC.
clock.
The clock. So the clock is saying do all this. Once the clock has done a full cycle, then it's going to move on to the next step. For my solution, I forget. like 20 lines of code right here, and then I changed what's in the test bench, and that was basically it. There was probably a couple other things I had to do, so I'm not going to guarantee that's it. But that's coding wise, you're just putting stuff in here, where you're instantiating modules, hooking up wires, calling it a day.
Just gotta print out everything.
Sounds fun.
It's definitely a different type.
That makes it sound a lot easier than it probably is.
The hard part of this project is
The
getting.
order in which we put the modules.
The order does not matter. The order is irrelevant because everything happens in parallel.
Oh, that's right.
Everything happens in parallel. You have no starting point. You could put the muxes in any order you want inside of those lines of code. It doesn't matter because it's all done in parallel. There is no sequential execution here,
So the
except in your
time's
behavioral modes, which we'll get to in a moment.
So we know we need 1, 2, 3, 4 muxes, but we need to know what mux we need at what point.
And what are the inputs, what are the
What are
outputs,
the
how do you set up those wires? You need to define a wire here, define all
Right.
these wires you need to define as well.
I need to find a store to go take this and just get it like load on day12.
All right. Hopefully we've talked briefly about behavior model. That's okay in a lot of Verilog simulations. This is the behavior. Whenever the clock goes up or the reset line goes up, you're going to begin to execute this code. Now, this is the few times in Verilog that your code is sequential. Every other time it's been parallel. Inside of begin and end, you may have something that is sequential. May, or may not.
Oh, great.
So this doesn't execute until a positive edge of clock or reset. What I first say is if it's a reset, aka the reset's high, set the PC to 0 and 1 to 1. Okay? And you're going to constantly execute this until finally the clock goes down and you can begin, the reset line goes down, you can begin the clock. So every time the clock goes up, that is going to signify the beginning of a clock cycle. So clock goes up, your clock cycle begins, you do your work, and then when clock goes back up, your next clock cycle begins. I have printed out some of the stuff for you already. You may use this, you may not, it's up to you. I highly recommend you use this. You may want to comment out a couple of display variables until you get things working. Notice that at the end, I make PC equals PC input. PC input is next PC is PC plus 1. So hopefully the PC counter is incrementing each time. I've actually set that up for you. PC currently increments each time.
So we won't really be changing the always clock, will we?
No.
We just only want the code above it.
Yep.
Just, okay.
But remember, I have PC equals PC plus 1. I haven't put in the mux for you. You're going to have to figure out how to do that. Also, I've already added the check for an halt instruction. If your instruction, INSTR, remember that was a wire up there, equals halt, I just say halt instruction encountered, exit the simulation, finish. So you don't need to write that either. I've written that for you. You just need to be able to hook up INSTR to be the instruction that you're reading from memory.
But
Okay.
then in that case, if you've already written that there, then we can get rid of the halt on the.
No, you can't
Oh.
because you have not hooked up. I have not written getting anything from instruction memory.
Okay.
I've only written PC equals PC plus 1 over and over again. That's the only thing I've done for you. You gotta do the rest. You got a question?
But I think I just don't really understand, I guess. But so is there any part of it where we'll be calling, like, is there any recursive part to this at all? Is it
Cursive part.
like, does it call itself, like, because it's a big circle, I guess? Or is it just kind of like a?
So remember,
it runs one.
remember everything's a bunch of gates, right?
Yeah.
So they're happening in parallel. The gates need to saturate, and your clock cycle you're using because you want everything to saturate within a certain amount of time before it goes back and executes the next thing,
So
the
the
next
clock
step.
cycle needs to be long enough.
Long enough, right? Because you will be updating your test bench to have a high clock cycle. You may want to just put in a ridiculous clock cycle at first, pound take 1,000, just to get something going, and then shorten it. That may be helpful, or it may not. It depends on how you wish to approach it. You really have to figure this out for yourself. Sorry, there's only so many hints I'm able to give you.
Well, no, at a certain point you go like, oh look, it worked for 100, but now it doesn't work for 80. Our problem is there.
Well, if you look at GTK wave, you'll see everything moving, and then when it stops moving, and then you have this long pause of
that's
everything.
gonna be my problem. I haven't
Everything's the
GTK
same,
wave
then-
work right.
Oh.
Yeah, we gotta get that working.
Yeah, that's gonna be.
And I'll show
I
you
had
all
it
again.
work for the
I'll
first
show you all
time.
again. It's
No,
we had it working for y'all before. It's not that hard. We'll get it going again. All right. Any questions about the processor? I'll talk a little bit about the components, but before I do that, I want to talk about the assembly, the assembler first. So let's go into the assembler. All right, in here on your code, you just have an A.C, which is my MIPS 32-bit assembler for y'all. Y'all don't need to mess with this at all. All you need to do is compile it. And then if you run it, it wants the assembly code and the machine code. Well, you also have, we'll go up a step. So in your assembler, you have that A file, that assembler I just compiled. You also have a programs directory with some different programs for you. If I were to open up programs first.s, hey look, halt. That's probably the first program you want to test, because this will test, can you actually exit this program? Now you're going to want to run a bunch of different other tests, adding, loading, so forth and so on. But one of your final programs should look something like this. You load in 5, -1, you start, you keep subtracting 1 from 5 until you're done branching, and then you halt. I do expect you to have a couple of extra programs to test besides this one, but once you're up to running this, your process is pretty close to being complete. Okay, so we have some assembly for you. How do you actually assemble it? Well, we got to, whoops, that was weird. Assembler A, that's the program. We'll call it programs. We'll do first.s into prg.bin. All right, that compiled the first.s into a program called prg.bin. Notice I put that right here. If I were to, we'll do head prg.bin. The first thing's the halt instruction, and then the rest are a bunch of zeros. That's all it's actually producing. The reason it's producing in this format is because then you're able to read it inside of your code. How are you able to read it? Well, let me go look in instruction memory. I've done this for you.
Yay.
Right here, readmin-h program.bin. So very important for your simulator to work. The program that you're testing has to be compiled to prg.bin. Your instruction memory will read that into memory. Your data memory is also going to read it as well. And then you can go on from there. All right. Do y'all see what's happening with the assembler and the whole tool chain to get the simulation going? Okay.
Nope. It says N-O-O-P.
Oh, I thought you said nope. I was like, what are you missing? That's a noop. No op. No operation. Nope. So instruction memory. Remember, you have an address coming in. Let me see, do I have that picture? Hey, look. Address coming in, instruction coming out. You have a reset and a clock line as well. That's it. How do I represent it? I make each word 32 bits, sorry, and then I have 64K of them. On reset, I initialize the instruction to a no-op, and then I read all program.bin in. That's it. Then whenever the address changes, or I'm on the negative edge of reset, aka we're lowering the reset line, we read the instruction from memory. I say it takes 20 ticks just to give it some time. And then I display it, of course, afterwards. Okay?
The negative edge.
That's when the reset falls, when it goes from 1 to 0.
Right at this point.
You may or may not. You need to set up your test bench so that the reset line goes to down to 0 the same time your clock cycle goes to 0 as well. Currently, that's what it's doing, but you'll probably have to mess with that a little as well.
Well, I thought you said you wanted to halt when you get to the full, when it starts to do the clock again. Or
You want it to halt when you have read the halt instruction. Okay?
When everything else is done.
Yeah. Well, single cycle, so once you read the halt instruction, the previous instructions have been completed, right?
Yeah.
Yeah, so you're good.
And the single cycle is done.
And single cycle's what?
Done.
Yeah. Yeah, you're
Well,
done.
we'll halt it before the actual cycle completes.
Yes, but that's okay because all your previous instructions have already
Have already
completed.
completed.
And that's fine. When we go to other processors, something else may happen. But in this one, once you finish completing your instruction, you then move to the next one. There's no parallelism between instructions with this processor because it's a single cycle processor. Okay, you see how instruction memory is reading it in, and then you're going to kind of need to plug it in and see what's going on. All right. Any questions about the high level of what I want you to do, the test bench, the processor, or instruction memory? I'm going to go into some of the different components just to show you how I did it next. But I wanted to see if there's anything high level here because that's the hardest part of this project.
I'm sure questions if we actually run into
Let's see. I'm sure I'll have questions later.
Thanks, Joe.
I'm just saying.
Just saying.
Yeah.
Yeah, I don't even know my questions until I get into it.
Yeah.
All right, let's go look at different components. And it's really hard to say what order they're in because everything happens in parallel, so I'll just do it in alphabetical order that they're listed inside of my directory.
Okay.
Adders. So I did the standard adder that we presented, and then a 32-bit adder is a ripple carry adder where I just generate 32 adders in sequence. All right, you may not have seen this code where I have generate. This is just how in Verilog how you can automatically generate a certain number of instantiations of a module for you. That way I didn't have to write adder F1, F0, F1, F2, F3, F4, blah, 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 blah. I just have it automatically generated.
Is that you just did a loop?
I did a loop. But the loop is generating the modules here.
Right,
It's
the
not,
loop is
I'm
before you
not
get to the
executing,
beginning.
yeah. I'm not actually executing a loop during runtime. Each of these modules have been instantiated and are running in parallel when you're going.
I wish we
So
knew that one.
the loop is right at that is in during the instantiation when you say okay.
Yeah,
instantiate all of these.
before simulation. Notice I put up my ticks up here.
Don't touch.
Yeah, no touching. All right, what else do we got? GVIM, the ALU. All right, you have your adder, and then notice I did a bunch with the NANDs. For EQ, I got lazy, and I just did an assignment with data flow.
Mm. If it works, it works.
All right, 6x64. All right, I wrote it out this way so it would be easier to read for you when you try and read this code. We could do a full decoder as it was presented, but that would be hard for you all to go in and read, so I did a data flow. Basically, when these bits come in, you are spitting out these, you are activating a certain line, and those represent different instructions. If you go back to the architecture, notice that the op or function is going into the decoder, and that decoder is then going to activate a line in the control ROM. So the decoder is taking your operation and activating a single line. That's what it's doing. Whatever the op is, a single line gets activated. Okay? Now, so I probably should look at the ROM next. ROM, depending on what line is activated, excuse me, we will activate the different lines for the different control points. 1, 0, 0, X, etc. Yes.
So what we'll need to do is pass the op into the decoder and then
Decoder then goes into the control ROM,
Yeah.
and then the control ROM is going to go to all these other components. that are
right, so
inside.
all of those with the red lines to them, all
Uh-huh.
the three muxes and the other three things, those have an op input that
They
we
have
need
a-
to pass.
Those have,
They have
these are the,
ROM
so
input.
the muxes are the select lines.
Yep.
This is an enable line, so forth and so on. And that's what's coming from your ROM over here. Notice your ROM is your
So
data
the
out.
output of that.
Yes, you need to
is
hook
going
up
be an
to your
input.
other modules.
Right, so Wait, it's coming from the what now? Go back to the.
Part of the instruction you need to forward to the decoder. That
Right.
decoder will then activate a line in the control ROM, and the control ROM will then set these control lines equal to what they need to be. 1 or 0, or in some cases, we don't care.
That's the control ROM right there.
That's the access.
This
That's
is-
the
yeah.
control- That's what we're looking at the control ROM right
Mhm.
now.
Hey, look, a hole.
Yeah.
So do you have like a MUX module?
Yes. Haven't gotten there yet. But yeah.
Working on it.
All right.
Data memory.
Sure, data memory.
We did instruction memory.
We did instruction. Data memory is very similar, except for now you have an enable line and a read-write line. Those are going to come from your control ROM, clock and reset, as well as NA and NB, depending on. NA should be the address, and B should be the data.
So the enable and the read write.
Yeah, so memory sub NA, your address, storing NB only if you've enabled the write, and only if you've selected write and the data memory is enabled. On reset, you just load in program.bit. That way you have all the default data values. Reading takes 20 ticks.
So the enable and the read write are both going to be from the.
Control ROM. All right. We talked about the MIPS 32 cycle. Oh, here you go. Here are the muxes. Hmm?
I said this seems possible.
Yeah.
It is.
You know what I mean? Like,
How our computers work.
like with everything with the input set up already. It
Yes.
seems possible to simply
We just
hook them
we
up.
just got to figure out.
You got to figure out how to hook them up.
I think we figured out the control ROM part.
We asked every question possible.
All right, mux. 2-to-1, 5-bit mux. So, hold on. Let's not do that one first. Where's the... Oh. Okay, I guess we are doing that. We got a lot of muxes.
Ooh.
We do have a lot of muxes. 2-to-1, 5-bit mux. A and B, notice they're both 5 bits. And then you have a selector wire to select which one it is. And your output's just going to be that one. Not takes 1 to not the S. And then we're going to generate the standard mux in order to select which one's which. All right.
Next.
2-to-1 32-bit mux. Notice you have 32 bits for A and B. Again, a selection wire. Oh, hey, look, it's the same thing, except for now you're generating 32 of these things as opposed to 5. Let's see, a 4-to-1 32-bit mux. Ooh, do we need this one? I don't know if you're going to need this one for this class. That'd be great if you don't. Notice you have A, B, C, D, and 2 selection wires, 1 output wire. Again, you set it up, and it's a little more complicated because you're selecting from 4 as opposed to 2, hence the extra delays in these ANDs. Because notice these are not ANDs with 2 inputs and 1 output, they have 3 inputs and 1 output, so they take longer to saturate. Same thing with your OR.
Places.
And then you have an 8-to-1 32-bit mux. I don't think you're ever going to use that, but I put it in here just in case you felt the need. Yeah, in case you really want it. It's the same thing except for 3 selection wires and again 32 of these. Obviously there's a lot more going on. It's really that final OR that slows everything down.
Where's
So
your
we're
module for
probably
your-
gonna
where's
use
your
the
module
ones
for your
with
2-to-1 32-bit.
What's that?
Your 2-to-1 32-bit.
Yeah, 2-to-1 32-bit is what you're going to be using a lot.
Yeah.
Okay.
And then what do we have here? 2-to-1 times 2, 32-bit. I don't know what that X2 is for. Huh.
I don't know. You wrote it.
Maybe.
Maybe.
Uh-oh.
Oh, okay. This is a different implementation in case you really wanted to compare
No,
them.
thanks.
This
I like
This- this one uses your previous muxes to implement it as opposed to generating them all. Same thing with this one, previous muxes. All right, we're done.
Okay.
What's next? The register file.
Oh, great.
All right, you have 2 read addresses. You have a write to address, the write data. Are you enabling the write? You have output, which is the value of the first register you read from. Out 2 is the value of the second register you read from. You have a clock and a reset line as well. Notice the reads are 5 bits, hence why you need a 5-bit mux right here, because you're only using 5 bits.
Hint, hint.
Whoa. Where you're writing it to, the data, are you enabling the write and clock and reset? Of course, your outputs as well. Register file, you have 32 bits per entry and 32 registers. Great.
I like that for write data, you literally just said write date and you just left out that last day.
Whatever. Right, Dad?
Right.
Nah, I was already tired of typing. We'll say reading from the register file takes 2 ticks. Sure, why not? On the positive edge, hey, look, writing is going to be instantaneous here. That's great. I guess I'm not going to put any delays on that one. And then when you reset it, we have the entire register file go to zeros.
Yeah.
All right, we're good?
Um,
Sure. What's left? We already talked about the ROM. Oh, sign extend. So sign extend. What's that? Hey, it's this guy over here. You have 16 bits. You want to move it to 32 bits so you can send it to the ALU. Input 16, output 32. We'll say it takes 1 tick. This is just how you type in Verilog. Extend whatever that first bit was to the beginning of it, and then just extend it out. Say it takes a tick.
Does it set everything else to 0?
It sets everything to the most significant bit. So if it was a 1, it's all 1s. If it was a 0, it's all 0s.
So you're assigning it, you're appending your input 15 to the 16.
Let me do it with 4 to 8. So if it was 0, 1, 1, 1, your final answer would be 0, 0, 0, 0, 0, 1, 1, 1. If your input was 1, 1, 1, 0, your last one is going to be first 1, 2, 3, 4, and then the end.
Right.
Like that. Okay? Why do we do it this way?
Hex.
Two's
Oh, two's complement.
Two's complement, yep. So this is just extending it to the standard negative number, just the 32-bit representation. Positive number to a 32-bit representation.
yeah.
Yeah! Okay.
Next.
I think that's it.
Oh. Wow. We're done.
Yeah, that's it. Alright, guys. Good luck. You have until March 19th to complete this. Again, just to be clear, the hard part of this project or this lab is figuring out what's going on. Because you have to, like I said, nothing's happening sequentially, so, well, they are and they aren't. There is a ton of parallelism going on throughout this whole processor. You need to think about how you hook everything up. There's not so much a start and an end point. In a way there is, because it's kind of how the instruction flows through it, but it's not officially a start or end because it's just one giant circle. So the hard part is figuring out what exactly is going on and then typing it out correctly and then updating that clock so that the values make sense and things are moving through. Another hard part is getting used to how that assembler works. I tried to keep it easy. Don't try and write anything complicated. Just keep it a simple assembler and things should be good.
Well,
Assembly files. Don't try and write real complicated ones. Just keep it simple, because that assembler was written particularly for this simulation. All right. Any other questions? All right. So we still have next week, right?
Yeah.
Yes.
Spring break.
Spring break, and we're doing the midterm afterwards. Is that right? Okay.
After spring break?
I
Yes.
thought we were doing a midterm at all.
Yeah.
That's just you talking to Matt too long. Okay, good. We'll do it after spring break. Do get started on this. What I'm really trying to say is that if you're looking at this for a long time and you haven't written any code, don't feel like you haven't done anything, because chances are you've done a lot. It's just you haven't shown you just haven't shown it yet, because it's the hard part is figuring out what's going on. All right.
Okay.
Everyone have a good weekend. I will see you on Monday.